a something like this. So D is a point on AC, and then E is a reflection of A on BB. Looks like we have another Con joining us. All right. Thanks for joining us, Con. Good to see you. So we were doing a bunch of hard questions, and now we want a little bit of an easier one. So, oh, it's you with a better mic. Okay, sorry. So I'm going to reflect A over BB. So that should give us a rectangle or a rhombus. I'm sorry, not a kite. So I mean, this almost looks like a square. So yeah, so here's E. And F is the intersection of CE with the perpendicular in D to BC. Okay, so this is F. And we want to show that AF, BE, and BC are concurrent. So yeah, this just showing that these, is this trivial? Let's see, I'm going to check the chat. This looks like it might be trivial. Yeah, definitely invite your friend next time if they're interested. Yeah, usually we have a couple more people, but yeah, sometimes just enough people can't make it. So, but yeah, I appreciate you sticking around. Yeah, otherwise I'd probably just do the session, do the rest of it myself. But yeah, I mean, if you have to go, feel free. But yeah, I'm glad you're able to stick around for now. So this looks like it might almost be easy because, I mean, we just want to show F is the reflection of B across BC, right? And the problem is equivalent to that because then it's true by symmetry. Actually, I'm not sure if that's true. I think it is though. Oh, maybe not actually. It might just be a trick. So if I move D around, okay, not necessarily. So yeah, F is not necessarily the reflection of B across BC. Okay, so we want to show that these concur. But I wonder if this, like if I label this point, I wonder if this is like an angle bisector right here. Oh, it's not. That's interesting. Okay. So yeah, so how do we show this? How do we show they concur? Like, can I just use, like, I think I might be able to just use Cheba's theorem. So if I draw this line, and I draw this line, and I let them intersect. So it looks like Shriyansh is back. All right. Hey, Shriyansh, thanks for joining us again. So we're doing a little bit of an, looks like an easier problem. So yeah, we'll see. And we just started it. Okay. So, okay, so I wanted to use Cheba's theorem. So I want to show, I think Shriyansh might have lost his connection. We want to show that AD over DC times CF over FH times, oh, actually, I don't know if we can just use Cheba's theorem, right? Yeah, not really. Can we use Desargues' theorem? AF, DE, and BC. How would we use Desargues' theorem for that? So that's the same as showing that ABE and CDF are perspective. That's one way we could look at it. Or ACE and BDF. We could show those are perspective. Yeah, this feels like projective geometry could be useful. So we want to show that if we project B, G, and C, then we get H, F, and C. Okay, so this is a kite. It's worth drawing this. And this is a right angle. So we know that this is cyclic. We have a couple cyclic quadrilaterals, right? We could draw all these points. We want to show A, G, and F are collinear. Actually, do we even need point H? I don't know why I drew that. Oh, because I was trying to use Cheba's theorem. But yeah, we don't need point H. This is all we need. And we have a lot of cyclic quads. This is cyclic. And yeah, it also passes through point I. And then this is cyclic, right? Or actually, I'm not sure. Never mind. This one was cyclic. That's what I was, or DJKI is what I was thinking. Okay, so we want to show A, G, and F are collinear. I mean, we could try to use Cheba on this triangle, right? So we want to show AD over DC times CF over FE times EK over KA is equal to 1. I kind of like that. We could also try to turn it into something about harmonics. So yeah, it looks like harmonics. Yeah. So we could also say, like if we intersect this with this, then we want to show F, C, E, and that point are in harmonic conjugation. Oh no, not that point, sorry. We would need like DK intersect. Yeah, it looks like harmonics, right? So yeah, what if we let DK intersect CE? And then we want to show that those 4 points are harmonic. But what will we project through? We can project through K or I. Yeah, we could try to project through I onto the circle. So let's try that. So yeah, I don't want to make it look like these intersect on the circle. Okay, so we want to show that H, E, F, and C are harmonic, right? That would prove that these all concur. And we could project through I onto the circle. And that's the same as saying that D, B, E, yeah, I don't know if that's the best idea. D, B, E, and that point are harmonic. Can I let KD? Yeah. So AD over DC, that's the same as DE over DC. Oh, maybe we want to project through K onto this circle. I'm not sure where F would go to, but yeah, I wonder if KF is tangent to that circle, and then maybe that would solve it. No, KF is not tangent. But let's see, we would have J, D, I, and this point, and we want to show that's harmonic. can we, yeah, what's a good point to project through? If DF cuts AE at X, yeah, okay, that might be a better, yeah. So instead of H, we could try to make point X. I kind of like that. So that's point X. And then let's see if we can project through something. Project through D. Oh, so yeah, that's the same as saying C, I, G, K are harmonic. Yeah. So yeah, I'll delete point H and F. Whoops, I'll just hide F. Well, F was part of the problem, so I don't know if I want to delete F, but H I can definitely delete. Okay, so we want to show X, K, EA are harmonic. What can we project through? If we project through point I, no, we could try projecting through D. So yeah, we want to show KIGC is harmonic. Is AC tangent to that circle? No. But F is projected at D from EC to AE. Oh, yeah, I see what you're saying. Yeah. So then we just show that's harmonic. So we know this is harmonic, A, B, D, E, right? From I, okay. Oh, that's trivial. Yeah. No, that's trivial because if we project onto this circle right here, then A and E stay the same. K goes to B and X goes to D, and A, B, E, D is harmonic. So that's trivial. Yeah, so that solves it. All right, so we solved this one. Okay, so now that we solved it, I'm just going to unhide F because, yeah. So, so ABED is a kite, and thus a harmonic cyclic quad. And then let AE intersect DF at X. And basically, yeah, we want to show that those four are harmonic. Oh, I should define point G. Let DE intersect BC at G. Actually, I don't even know if I need that. I just need to show, yeah, so then let I be the foot of the perpendicular from D to BC. Let's unhide H. Oh, wasn't H this point? We don't need that point, right? This one? Why do we need that one? Oh, but we're instead showing that XKEA is harmonic. We don't need to show that HKEA is also harmonic, right? Like it's enough to just show that XKEA is harmonic, because that would prove that AF, DE, and CK concur. Oh yeah, that's all right. So we have so let AE intersect BC at K. And then projecting through I onto the circle ABED. Then we have AEKX is equal to AEBD -1. And then once we know that, so that implies that AF, what is it, CKAF and BE concur. Which is the same as saying AF, DE, and BC concur. Well, I might as well just say that, yeah. That's good enough. All right. A, F, D, E, and C, I'll say CK, but it's the same thing. All right. Sounds good. So yeah, thanks for the idea. Oh yeah, this problem, I forgot where I got it from, but it's kind of interesting. This problem actually looks a little bit easier too. So I'm going to write the problem statement. So basically in triangle ABC, let D be the foot of the altitude from A. D be the foot of the A altitude. And then let E and F be the feet of the altitudes from D to AB and AC. And let BF and CE intersect at S. Prove that the circles SEF and the circle centered at A through D are tangent. So yeah, I forgot what source I got this from, but I am not going to look it up right now, but it looked interesting. So, and another thing I noticed is that it looks like DS passes through the point of tangency, although I couldn't prove it. So yeah, let's see if we can solve it. One sec, I'll be right back. All right, I'm back. So yeah, we can kind of rephrase this problem. We could hide this circle, and then we want to show GESF is cyclic. One sec, I'll be right back. All right. Yeah, first we want to show GESF is cyclic, and then we want to show they're actually tangent at G. I think this actually might be a somewhat hard problem, to be honest, but I'm going to keep trying for a little bit. So maybe it's worth drawing AG. You created your own problem? You want me to try right now? Okay. All right. Okay. I should be able to see the link. Let's see. Yeah. All right. So I'm going to copy paste what you put. Let's try it out. So the circle is centered at O and radius OH. Okay. I don't think I've seen a problem like that before. Let me try it. Okay, so this is from Trin Kwok Khan. The next session? Okay. All right. I will do that. Let's see if anyone had said anything in the Discord. Yeah, I guess just no one was able to make it. All right. So let's see if we can solve this. We have about an hour left. So yeah, how do we show GESF is cyclic? I'm just going to draw in the circle. Maybe it'll help. All right. Thanks. It almost looks like, I don't think DE and DF are tangent to that circle. No. So yeah, basically we want to show there's a homothety at G taking one circle to the other. We know AEFD is cyclic because it has two right angles. And AD is the diameter, so we know it's tangent to BC. Yeah, so yeah, maybe this is like because isn't there some kind of theorem, like if you have a homothency from one circle to another, and then you have a homothency from that circle to a third, then there's some homothency taking the first circle to the third? I think there's some kind of theorem like that, right? Some kind of special homothency. Let me see. So this would be the center of that homothency. So, oh yeah, basically by Monge's theorem, these three are going to be collinear, right? So G, D, and H are collinear by Monge's theorem. How does it make no sense? Or why does it make no sense? Oh, there's just no way we can use that point. Okay. Let's I'm just gonna check that really quick. See, is like, does AH pass through this, or that's probably a coincidence? I don't think that's true. Yeah. There's no way that's true. Yeah, okay. So yeah, I'm gonna delete that. Let's see. What if we draw the center of this? I would be very surprised. Oh, does it really lie on AG? Interesting. The center of this circle, it looks like it lies on AG. Oh, but that's obvious. Well, because these are tangent. Yeah, I think it's obvious. Yeah. If the problem's true, it's obvious. Otherwise, it's not really. Okay. It almost looks like G lies on AC, which doesn't. So I'm going to try to draw it a little bit more like that. Yeah, it looks hard. But it's such a simple, right? There's not much to the problem statement. It just looks really hard. I'm going to keep trying it for a little bit. Let's see. I don't know, maybe if we draw the tangent line, it would help to both circles. I wonder if B, C, and EF concur. Yes. Oh, it looks like they do. That might be really helpful. Yeah. So let's draw this point right here. And okay, so basically, let's Yeah, I'm not sure how we want to define this point. Do we want to let EF we want to define it this way and then show that it's tangent to one circle and then the other circle? Yeah, there's a lot of things we have to prove. First, let's see if we can prove that it's tangent to this circle. So I'm going to hide this one. And then, yeah, so basically we want to show S lies on the polar of H. So I'm going to hide this. Can we show that S lies on the polar of H? Well, that's the same as saying that this cross ratio, saying that S lies on the polar of H. Oh, I would have to draw this line and show the cross ratio is 1. So we know, let's see, is GFDB cyclic? Yes. How did you figure that out, or did you just try to check it? And then that means that GEDC also has to be cyclic. That's a good observation. How did you figure that out? Did you just try to check it? Ah, interesting. Oh, because if these were collinear, yeah, then yeah, you might be able to use power per point. Well, that would mean BEFC is cyclic. Is that obvious? Or I'm not sure, but I think it might mean that. Yeah. Yeah, that's just obvious by an angle chase, right? Because this angle equals this angle, which equals this angle. Okay. So, oh, and then we just have Brocard's theorem, right? So, basically S, yeah, let's draw the center of this circle. I think we're making progress here. Call that J. And so SJ is perpendicular to AH by Brocard. HE times HF is HB times HD. which is hg squared, or hb times hc. Wait, how do you know hb times hc is hg squared? Oh, that's all right. Let's draw HS for a second. Oh, I think S lies on the radical axis of these two circles. Yeah, it does. So basically, we can then draw in, it's all right. Yeah, we could draw in these 4 points. And then I think we might be able to show that S lies on the polar of H. So we have this point, and then we have another point. This point right here. So S, yeah, I like this. I think we're making progress here. So and then basically, so we want to show S lies on the polar of H. That's the same as showing that those are in harmonic conjugation. And then once we know that, we would know that DS and G are collinear. Yeah, basically, yeah, we use the radical axis theorem on the 3 circles in the picture. But we still want to show AD cuts the circle J at X. So HX is tangent. Okay, so I'll call it X. Wait, are you sure about that? HX is tangent to, I think it intersects at another point right here. Yeah, it's all right. But is X the midpoint of AD? I think it might be. Oh, I think it's slightly different. Yeah, they're not the same. Okay. So another thing that we could try to show, if we let BK intersect CL, basically we want to show that AS and that point are collinear. That would be equivalent to showing that S lies on the polar of H. All right. Looks like we have someone else from Vietnam. Chia. So thanks for joining, Chia. So yeah, this is a problem I saw recently. I'm not sure what the source is, but it looks really interesting because it starts out as an easy problem, but it looks like it might be a little bit harder. Hey, Con. Ah, nice. Your class ended early, so you could come on earlier. Nice. Thanks. Glad your class ended early so that you can make it. Yeah. Yeah, so this looks like a fun problem. So we added a lot to the diagram, but originally it's just a ABC, and then we basically drop an altitude from A, so D is the foot of the A altitude, and then you drop the altitude Z and F from D, and BF and CE intersect at S, and then you just want to show that these two circles are tangent. So SEF, so I hid that circle, but it's this circle right here, and the circle centered at A through D. Oh, Buratino created this one? Then it must be hard, right? Do you remember the solution?
Actually, this is for grade 10, I think, because I saw it somewhere, but I haven't done it yet.
Okay. All right. So it's grade 10, so maybe it's not as hard. Are SD, I don't know why I didn't see this. Are these, do these pass through J? Yeah. So
we can prove that by using Pascal.
By using Pascal's?
Yeah, SDJ are collinear by Pascal.
Okay.
Maybe can you draw the diameters?
Yeah.
The L prime and
L prime?
L prime and KK prime.
Okay. Hold on one sec. I'll make the diagram smaller. All right. Okay, so that's one diameter and this is another diameter, right? Was that what you want?
So DE and L prime must be collinear.
DE and L prime?
Yeah, because DL is 90 degrees.
Oh, yeah.
So then you just use Pascal for those 6 points on the circle.
Okay. And then DF and K prime. Wait, so
I think F. I think it must be F prime, not KK prime. I think.
okay.
Yeah.
Yeah, I was gonna say.
Sorry.
It's all right. All right. Okay, so Oh, I think it's, you mean C prime, right? And B prime. Yeah.
Yeah, I think I messed up one more time. Yeah, it must be
That's all
B
right.
prime CC.
It's okay. So yeah, by Pascal, S, D, and J are collinear. And then, yeah, can we show that? So we haven't really said how we define G yet, because we don't know the circles are tangent. But it looks like S, D, and J pass through that point. So yeah, I was thinking about hiding the circle SEF for now. And basically, can we show that S lies on the polar of H so that G, S, and B would be collinear? Yeah, that's what we were trying to show before, but I haven't been able to figure it out yet. I can change this to Buratino.
I think I can solve this one. So
Okay.
let's redefine point G.
Mm-hmm.
So I will let SDJ meet the circle center at A at a point G.
Okay.
Yeah, SDJ. Yeah, earlier we proved that they are collinear. So just connect them. Yeah.
Yeah.
And we can prove that BEFC is cyclic. So by the Brocard theorem, we have SJ is perpendicular to AH.
Yes. So yeah, SJ is perpendicular to AH, so they intersect on this circle.
Yeah.
Okay.
And since AG is equal to AD, we must have HG is the tangent.
Okay. I like
Yeah.
that.
So I think this somehow gonna solve it.
Okay.
Maybe.
So yeah, so now we basically know S lies on this line. Yeah, because it's by symmetry since it's perpendicular. Yeah, I missed that before, but yeah, that's a good point. Okay. So yeah, now we have to show that GESF is cyclic and it's also tangent. So I guess once we show it's cyclic, it would follow that it's tangent because we have HE times HF is HB times HC, and I think we could show that's HD squared, which is HG squared. So wait, so I think AMBC is cyclic actually. Yeah, can we prove that? Is that obvious? Yeah, no, that's true. That's obvious because
We can use power of a point.
yeah.
HA is HD square is HE times HF is HB times HC.
See, so yeah. So power of a point would prove that that's cyclic. I don't even know if we need that circle though. That might have just been something extra. Okay. Oh, thanks for joining, Robbie. Sorry, I saw you came in later, but yeah. All right. So yeah, we just need to show that that's cyclic, and then, okay. I wonder if HK is tangent to that circle. So let's unhide it. No, I don't think HK is tangent to it. But yeah, Brocard's theorem, yeah, it was a pretty powerful tool here. Pascal and Brocard's. Okay, so yeah, there's, how should we show it's cyclic? We could try an angle chase. We could try power ratio lemma, power of a point. What's another way we could do it? Homothety, we could, yeah, maybe homothety is a better way to do it. So but yeah, it would be a little tricky to draw. I don't think these concur. No, there's no way that concurs. But basically, I mean, the homothety would take S to D, right? So yeah, like I don't know if I could draw the parallels through D to SC and SF. I don't know if that would really help much. And then maybe I could use the other homotheties. So
Wait. Did you prove that SLK are collinear?
that S, what points? SL and K? Yeah. Well, yeah, I proved that these are all collinear. HLSK.
Oh, so then we just need to prove that GESF is cyclic, right?
Yeah, we just need to prove GESF is cyclic.
Okay.
Yeah.
Okay, so we can do this by angle chase and power over point.
Okay.
So you have SLKR collinear. So we have SG times SD. It is SL times SK. And SL times SK is SE times SC. So GEDC is cyclic.
So okay, so GEDC is cyclic.
So angle GEGD, you can see that angle EGD is equal to ECD equal to EFS. Yeah, and we finish.
Okay, very nice. So I'm going to type this up. I like this. All right. So yeah, there are a lot of different things in this solution. So let EF intersect BC at H. Okay. And then, okay, so first we claim that BEFC is cyclic. That's just an easy angle chase, because basically angle AEF equals angle ABF equals angle ACB. So yeah, so so yeah, first angle AEDF is cyclic. So we have angle AED is angle AFP is 90. So that means that AEDF is cyclic. And then we have angle AEF equals angle ADF equals angle ACF. And that means that BEFC is cyclic. And so let J be the center of that circle. Okay. And then let B prime and C, let B prime and C prime be diameters. Okay. Then FDC prime and C prime are collinear. BFC equals 90. And so are E, D, and B prime. And then by Pascal's theorem, S, D, and J are collinear. All right. And once you know that, let the line SDJ meet this circle at M and the circle through A. I'm just going to call it omega in the problem. I'm going to cheat a little bit. Let the line SDJ meet omega and an AEDF at G and M. And then by Brocard's theorem, JS is perpendicular to AH. And then that means that HG is tangent to omega by symmetry. What did I just do here? HG, I gotta put another $sign. And then once we know that, Yeah, I don't even know if we need K and L. So first we wanted to show that GE DC was cyclic, and that's true by power of a point because wait, now I'm trying to remember. Oh, because we showed that GS times SD was ES times SC. That's how we did it. Okay, so so we have GS times SD. Oh, we needed that it's LS times SK. Did we need that step? Oh, it's all right. We tried two harder problems. Like we tried, so we solved the first one. We found a solution using a lot of ratios, but I feel like there's probably a better synthetic solution. And then this one, look, this one we didn't solve. This one we didn't solve. This we didn't try those, but then we solved this one. And then now we did this one. So those, yeah, those are all the ones. So I'm trying to remember, how did we show that this was cyclic? We said that ES times SC is BS times SF. So after, once I finish writing this up, I'll look at one of the old previous problems. But I'm trying to remember, so con, how did we show that GEDC was cyclic?
I'm sorry, what? GE what?
GEDC.
We use we have SG times SD is SL times SK.
SL times SK. Okay. And then
it is it is equal to SB times SF.
Okay. So and that which is SE.
But we have to prove that S lie on the radical axis of
Yeah.
those two. So yeah, anything is not hard.
Okay. Yeah, S lies on the radical axis just because it has the same. Well, yeah, we could just use the radical axis theorem on this circle, and this circle. So, so let omega and BEFC intersect at K and L. So let C and then basically, so yeah, I'm gonna just try to write this up as quick as I can. So by the radical axis theorem on omega AEDF and BEFC, then we have H, L, S, and K. Well, we have H, L, and K are collinear. But it's easy to see that S also lies on that, right? Because S has the same power with respect to those two circles. So first I'm going to say H, L, and K are collinear. But then at the fact that S lies on it, that just means S has the same power with respect to those two circles. Actually, yeah, how do we show that? How do we show that H, L, S, and K are collinear? So we want to show it has the same power with respect to this circle. Well, so maybe we can use
I got it.
Brocard's.
I got it. Yeah, Brocard. Yeah, exactly. We have by the Brocard theorem, we have A lies on the polar of S. S must also lies on the polar of A, and we can easily show that LK is the polar of A. So S must lie on LK.
Okay, so A lies on the polar of S with respect to this circle. Okay, so A lies on the polar of S because yeah, ds times dm is dA squared. Is that right? So so okay, by Brocard's. So yeah, by Brocard's theorem. So JS, yeah. Well, by Brocard's theorem, I'll just say S lies on the polar of A. Yeah. Yeah, I'm just going to leave this, but yeah, I think it's easy to see. So that means that H, L, S, and K are collinear. And then you can use power of a point. So okay, so SL times SK is SE times SC. Well, so SG, first of all, so yeah, it's SG times SD. And this is SE times SC. And that implies that GLDC is cyclic. So SGS or GEDC is cyclic. Okay. And then we do an angle chase to show that GESF is cyclic because then angle SEG equals angle SGE equals angle DGE, which is equal to angle DCE, which is equal to angle DCE which is BCE angle BFE, and that means that GSEF is cyclic. Or GESF. Yeah, okay. And then it's obvious that those are tangent because HG squared is equal to HD squared, which is equal to HE times HF. This is like power of a point so many times, and yeah, implies so SEF and omega are tangent at G. All right, so that is the last line of this one. So I'll go back to some of the previous one of the previous ones we did. But this is a cool one. We got Pascal, we have Brocard's theorem a bunch of times, and power of a point a bunch of times. So yeah, either this one or this one looks like it might be easier. I don't know, but it's still not that easy. So we have a triangle ABC. So I is the incenter, O is the circumcenter. And then I feel like I've seen this in a bunch of problems where H is the orthocenter BIC, right? Isn't that like a common configuration where you take the orthocenter of BIC? I think I've done it on my channel a couple times. I think there's an interesting lemma. Actually, if you make a parallelogram like BHC and another point, I think there's like something special about that other point. But I forgot. Anyways, so so E and F are the points of tangency. I guess E kind of, I don't know where E went, but we draw. So basically, S is the intersection of AEIF with the circle, and T is the intersection of the circle AIO with the circumcircle of ABC. We want to show ST HI is cyclic. So yeah, we added a couple points to the diagram. Like point X, we added S is the Sharkey devil point. So yeah, we added a couple things. I think this is an isosceles trapezoid right here. I don't know if that helps, but yeah. So yeah, I'm not sure. Yeah, we want to use like an angle chase or power of a point, or yeah, how we want to do it. Since this is the Sharkey devil point, yeah, I don't know if we want to drop a perpendicular from D to EF or intersect EF with IS. I really have to go after at 12 today. I'm sorry, but I'll send you this file, and we can go over it next session too if you want. But I have an event that I have to go to like right after this. So yeah, I'm sorry. Do you want to go over it next time, or do you want to try to figure it out after the session? Okay. So yeah, we could, yeah, I'll take a look at this maybe later tonight. But yeah, I know it's late for you guys. So yeah, I appreciate that you come on so late. So yeah, there's this problem. And then the other problem, let's see. Yeah, let's just do this one for the rest of the time. So yeah, we have the circumcircle of AIO, and it meets it at T, and then we have the circumcircle AEIF, and it meets it at S. And we just want to show that THIS are cyclic, where H is the orthocenter of BIC. All right. So yeah, maybe I could let TS meet this at a point and then try to use power of a point. I'm not sure how helpful that would be. But is there anything special about IS? So if we let IS intersect EF, then by the Sharkey double stuff, we know that like this point's perpendicular to EF, right? So we know DN is like parallel to AI. I don't know if that helps. I wonder if TN and D are collinear. No, they're not. Does TW intersect on this circle? No, it's just a coincidence. All right, a couple more minutes. Let's see if we can think of anything. So yeah, I know IL is parallel to BC. That's like part of the Sharkey double configuration. I wonder if I draw AT. So let's see. I wonder if we have anything occur. sorry. Let me rename this. That's weird. It won't let me rename it. Huh. That's so weird. I can't rename E1. Isn't that weird? Like it'll let me rename other points, but it won't let me rename E1. Oh, I could try it right here. See. Now it says E2. That's so weird. Okay. All right. So I'll have to head to another event, but yeah, thanks guys for hopping on. Yeah, even though it's close to the end of the session, yeah, I still appreciate that you guys were willing to join for a little bit. And yeah, thanks Con. So yeah, both of you for coming up along. So if for everyone watching, if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of my video. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.